All right, guys, so let's see. I guess maybe I'll start off with a little bit about the midterm. We're trying to grade it right now. Well, the TA, Madura, she's grading it. I don't have to grade. That's her job. But if you were, kind of wondering about whether you should drop the class or not, and maybe how you did on that midterm will affect that decision, I can't promise grades will be out by midnight tonight, but we've been trying to get them graded as fast as possible. But, if you are on the fence about it, then you can still kind of tell, like, if that midterm was really hard, if there were problems that you didn't know how to do, maybe multiple problems, then that might be, a bad sign that maybe this class is not right for you. I'm just curious, anyone in here thinking about dropping? Okay. And I do want to apologize if there's anyone here that had to sit on the stairs because there wasn't room. Like, maybe I can be forgiven for thinking that we had enough room in this classroom. Like, look, this place is like a third full, right? And I don't think I've ever seen it even as much as half full, except we have a midterm all of a sudden. Now there's not any seats. So let me just say a message not to you guys sitting in front of me, but to you guys watching at home. You might want to try showing up at class a bit more often, especially if the test was hard. Okay. So let's see. Anything else there? All right. So let's pick up where we left off on Monday, which was doing complex numbers, which are really cool and really fun. Okay, so one of the last things that I drew on the board I'm looking at the complex number z equals a plus bi. And what I'm drawing here, if this is the number a in the plane, and this is the number b, this should kind of remind you guys of learning about polar coordinates. If I then want to start talking about what is this length right here? So if that distance is r, just like we were doing in polar, well, then I was able to show that r, which is also called the magnitude of z, you can write it as the square root of z times its complex conjugate, or if that's the same thing as by the Pythagorean theorem, square root a squared plus b squared. So you can see why we decided to do complex numbers right after we did all this business with polar coordinates. It's very, very related. And that's, of course, the radius. I should also talk about the angle. So, all right, here's this angle, which we'll call about theta, like usual. So let's see. Theta, by the way, we have a special name for that we haven't really used this term before in polar coordinates, but in the context of complex numbers, theta is called the argument. The word argument has different meanings even in math, but in the context of complex numbers, it's the angle that the complex number makes with the positive axis, the positive horizontal axis in the so-called complex plane. That's what this is called, by the way. The complex plane is pretty trippy. Like, you can do a lot of the same stuff in it that we did in the xy plane, but it's got a little bit more structure. So you'll kind of see what I mean. For example, adding two complex numbers. I already showed you that a plus bi, this is some complex number, and if you add some other complex number, well, you just add the real parts and add the imaginary parts. But that's just like adding vectors in the plane, right? If this is a plus bi, and this guy is c plus di, then let's see if I can draw this. I need to pick this and draw it right here. So it's kind of like you put this vector tip to toe with this vector, and the place where we end up, this guy is the vector sum. It's the sum of these two complex numbers. So a plus c plus b plus di. Okay. As we also know from dealing with polar coordinates, oh, in fact, here. So I'm still referencing this image right here. So in this image, r is the magnitude, theta is the angle. We can say theta, no, let me say tan of theta is equal to the opposite over adjacent. So that's b over a. And we could also get a and b in terms of r and theta with the familiar formula. A is r cos theta, and b is r sine theta. Okay, so this should all look very familiar, but now let me do something with these two formulas to sort of put this number in a different form. So z, which is a plus bi, according to that, that's r cos theta plus I times r sine theta, or if I factor out the r, it's r times cos theta plus I sine theta. So this is such a useful way to write a complex number that it has its own special name. That's the polar form of z, which is a plus bi. So here, let's do an example. How about? And it should really just remind you of polar coordinates. It's the exact same type of calculation. So let's put, how about the number 5 plus 5i in polar form? And, I usually like to draw a picture. So let's draw a picture of this. Let's see, here's the real axis. Here's the imaginary axis. So let's go up 5 on both of those to put us right here at 5 plus 5i. What's the angle, how about? Pi over 4, good. Theta equals pi over 4. Okay, and the radius, that'll be the square root of 5 squared plus 5 squared, according to this formula. So that's the square root of 25 plus 25. It's the square root of 2 times 25, which is 5 root 2. So the polar form of z, okay, this was our radius, so 5 root 2. Right, I'm plugging into the polar form equation, times cos pi over 4 plus I times sine pi over 4. Great. Okay, now that's all fine and good. That doesn't really do much for us here, but pretty soon you'll see like all the sorts of neat things that writing a number in polar form allows you to do. In the meantime, before we get to that though, let me just show some other properties of what happens when you write complex numbers in polar form. Like back on Monday, I showed you how to multiply two complex numbers. but that was using the rectangular coordinates. So now let's do the same calculation, but using the polar coordinates. So how about z1, which is r1 cos theta 1 plus I sine theta 1. And z2, which is r2 cos theta 2 plus I sine theta 2. And let's see what happens when we multiply this. Let's see. Z1 times Z2. So I'm going to write the R1 times R2 in front, and then I'll have a cos theta 1 plus I sine theta 1 times cos theta 2 plus I sine theta 2. Okay, and now let's just distribute all this stuff and simplify. I'll get a cos theta 1 and a cos theta 2, and then minus sine theta 1 sine theta 2. And then I'm going to get an I times, let's see, this one times this. That's sine theta 1 cos theta 2. And then this one times this. Cos theta 1 sine theta 2. And what do you know? This is able to be simplified with a trig identity, actually. Yeah, so it helps if you remember your trig identities here. This is the same as R1, R2. Who recognizes what's this one? I expect some of you guys, in fact, I would hope all of you put this on your cheat sheet when we had the test, because it could totally have come up. I don't think it did, but it could have on the test, right? It's not easy to remember. This is the angle addition formula for cosine. Yeah, theta 1. That's cos of theta 1 plus theta 2, actually. And how about this one here? It's the one, yeah, angle addition for sine. That's sine of theta 1 plus theta 2. So this whole thing gives me cos of theta 1 plus theta 2 plus I times the sine of theta 1 plus theta 2. Okay, here, you can keep that if you want, but it's kind of easier if you just remember what happened, or in fact, here, maybe I can draw it. Like, what happened to the magnitudes of the resulting product? The magnitude of the product was the product of the magnitudes, right? This here, the magnitude, it was just the product of the original two magnitudes. So that's kind of like what we would expect for multiplication. You just multiply the magnitudes, but the angles added together. So I kind of would want you to just sort of like think about what this means. The resulting magnitude, it was the product of the original two. Well, the angles were added together. So it's like it scaled up the length and then rotated the angles, or just added together the angle. So, like for example, what if one of the numbers was on the, I guess I can call it the unit circle, meaning the magnitude was 1. So this is going to be important later, so let me just point this out. If, say, one of the numbers had magnitude 1, meaning in the complex plane, right, this is 1, I, -1, -I. This is like the unit circle, but in the complex plane. Oops. So numbers that are on the unit circle in the complex plane are actually of particular importance. And we're going to, like I said, we're going to see more of those coming up soon. But if this was our, what I called Z1, which if you let the magnitude be 1, this number basically just goes away, and it's simply equal to cos theta 1 plus I sine theta 1. Multiplying by Z1, all it does is just rotate you in the plane. Right? If I take some other number, whatever it is, Z2, and if this number, this is the theta 1, the argument of Z1, multiplying by Z1 just rotates this by an angle of theta 1. So I'll get the same vector, but rotated by that angle, theta 1. It's kind of neat. Multiplying by numbers just rotates you around. Okay, so we're going to come back to more of these numbers on the unit circle, but with regards to multiplying, how about if I divided? So Z1 divided by Z2, you might guess that if multiplying them would multiply the magnitudes and add the angles, dividing them should divide the magnitudes, and what about the angles? Subtract the angles, yeah. So that'll be cos of theta 1 minus theta 2 plus I sine of theta 1 minus theta 2. Okay, so if I want to apply this multiplying formula, let me use that multiplication formula, and let me suppose, so what if I let Z1 equal Z2 in that formula? So in other words, I want to calculate Z squared, which is Z times Z. And according to that formula, that'll be, well, R times R, and then cos of theta plus I sine of theta plus theta. Right, here Z is equal to R, cos theta plus I sine theta. So R times R is R squared. Theta plus theta is 2 theta. This is just what we get from applying that multiplication formula. The reason I showed you this is because maybe now you can guess what the formula for Z to the n should be. Z to the n, Right? Okay, like this was z squared. So you can kind of guess, well, how about instead of a 2 right here, and here, and here, and here, z to the n, let's just put an n there. So it's r to the n cos n theta plus I sine of n theta. And this is actually pretty amazing because this gives us a much simpler way to calculate numbers if we didn't know this formula. Like, let me give you an example. Here, can you guys, if you need the SI times, can you copy these down so I can erase that part of the board? All right, everyone good? So, for example, how about calculate root 2 plus I root 2 to the 4th? And like, if we didn't have this formula, we would have to multiply out a bunch of terms. It would be kind of a pain. But using the formula, using the polar form, let's see. If z is root 2 plus I root 2, so the magnitude of z, that'll be the square root of root 2 squared plus root 2 squared. That's the square root of 2 plus 2, which is 2. And the angle, hopefully by now you guys know that if this is root 2 plus I root 2, this angle here is pi over 4. So z, I could also write in polar form. I have my magnitude and angle, so that's 2 times cos pi over 4 plus I sine pi over 4. And I'm asked to calculate z to the 4th. Well, let's just use that formula. So that'll be 2 to the 4th. And cosine of 4 times pi over 4 plus I times sine of 4 times pi over 4. So that's 16 cosine pi plus I sine pi. Sine pi is 0, and cos pi is -1. All right, so this is 16, well, times -1 plus I times 0. So that's 16 times -1, which is -16. Okay, so this probably would have taken a lot longer if you actually tried to, like, FOIL this out, and you would have had 4 different terms. And you can imagine, I could have, like, given you a much bigger number right here. I could have given you 40. And it would have been pretty easy to do just using the polar multiplication formula. So this is good. This is going to save you guys time. It's kind of a neat shortcut. And it's going to allow us to do even more than this. But let me point out, so now that I've done powers, I gave you this power formula, the next natural thing to do would be roots. And there's one tricky thing you have to watch out for when you're doing roots of complex numbers. And I didn't mention it before when I talked about the polar form of a complex number, But I did mention it when we did polar, which is that speaking as angles, you can always add 2 pi. And as angles, that's the same. It's the same, you get the same angle. So as angles, theta is always equal to theta plus 2 pi. In fact, any multiple of 2 pi, any integer multiple, for all integers k. Can you guys read that? Yeah, this board's kind of messed up. Okay, so this equation it's not true as numbers, but it is true as angles. You can always add 2 pi and get the same angle. And that's going to be a crucial fact for what I'm about to do, which is calculate the nth root of a complex number. So, and it's going to have kind of a neat implication. So, roots. Here's the question. What is the nth root of some number z, which I will write in polar form, because that's the form we need it to be in to do all these calculations? In other words, what is the complex number w such that w to the n is equal to z? So, okay, let's try and figure this out. First, let's write w. We don't know what w is yet, but whatever it is, it can be written in polar form. So let's suppose w is equal to, how about s cos of phi plus I sine of phi, right? So here, s is the magnitude of w, and phi is the argument of w. Okay. Using the power formula, I'm going to plug in to this equation here. So w to the n, it'll be s to the n, cosine of n times phi plus I sine of n times phi. And we want this to equal z. So equals, z was r times cos theta plus I sine theta. Right? This equal sign is what says I want w to the n to equal z. Okay. Well, the only way this complex number equals this one is the two magnitudes have to agree, right? Like if they're equal, they're both the same distance from the origin. So this quantity has to be the same as this quantity. They have to be equal, right? S to the n must equal r. And that's not so bad because these are both positive real numbers, right? So that tells us right off the bat what s is. It's r to the 1 over n. That's fine. Again, these are both positive real numbers. So that's fine for the magnitudes. It's kind of what you'd expect, actually, right? Nth, for the nth root, well, just take the nth root of the magnitude. Angles, though, are the trickier part. And you're going to see why I'm going to need this fact right here for the angles. So for the angles, I'm going to need, like this, as an angle to be the same as this. And similarly, this the same as, well, whichever one you want to look at. The angles need to be the same, right? This guy, as an angle, needs to be the same as this one. So we need n times phi to be equal to, so I'm going to say theta or any multiple of 2 pi difference of theta. That's the crucial part here. So plus 2 pi k. So phi, it's theta over n plus 2 pi over n times k. So I didn't just get one angle. I actually got a variety of different angles. And you can see, like, I'm going to get different angles depending on what the integer k is. Like, so if k is 0, I get theta equals, I get phi equals theta over n. If k is 1, then phi, it's theta over n plus 2 pi over n. If k is 2, I get theta over n plus 2 times 2 pi over n. And I can keep doing this all the way up until, so here, look, if k is equal to n minus 1, then I get phi is theta over n plus n minus 1 times 2 pi over n. What happens if k is equal to n? Then I get theta over n plus, well, n times 2 pi over n, and the n's cancel. This is finally what happened here on this angle. We already did this one. That was the same as the very first one. So actually, I don't need this one. We already did it. That's the same as k equals 0. But all the others are distinct angles. The point here is, if anyone was counting, how many different roots did I get? Or how many different angles did I get here? 1, 2, 3, all the way up until n minus 1, starting from 0, that's n different roots. So it should actually kind of make sense. Like, remember when you would take the square root of a number, you would get plus and minus, the 2 square roots. So for square roots, there are always 2 roots. Well, it turns out that now that we're allowing complex numbers, cube roots, there will always be 3 of them. Fourth roots, there will always be 4 of them. Every number will now have n distinct nth roots. We get n different roots, i.e. w is equal to, what was it, r to the 1 over n times cos of theta over n plus k times 2 pi over n plus I sine theta over n plus k times 2 pi over n for k equals 0, 1, all the way up until n minus 1. So these are the n different roots. Any one of these we could call z to the 1 over n. Right? It's kind of bad notation. Z to the 1 over n, I could say it's equal to any one of these numbers, and those would all be correct. Usually, like, we pick the simplest one, which is the k equals 0 one. So I kind of lied to you back over here when I said, where did I lie on this board? I said, what is the nth root? I shouldn't have said the, because there's n of them. So what are the nth roots? What are the complex numbers w such that w to the n is equal to z? Okay, here, let's do an example with that. Here, okay, so let's use this one. So this one, we calculated this was negative 16. So here's another example. If z is equal to negative 16, let's find the fourth roots of z. And we already know one of them. It's going to be this one. So, all right. First, we want to write it in polar. Here's the point negative 16 in the complex plane. So writing negative 16 in polar form, what's the angle? Pi, good. So that's 16 times cos pi plus I sine pi. Okay. So now let's use that formula. So the fourth roots are, it'll be a 16 to the 1/4, and then I'll get a cosine of pi over 4 plus k times 2 pi over 4. I sine pi over 4 plus k times 2 pi over 4. So here, let's write them down for the different values of k. So here, if k is 0, then I get (16 to the 1/4), by the way, is 2. So if k is 0, I'll get 2 times cos of, well, pi over 4 plus I sine pi over 4. And I want to draw these in the plane because there's a neat, like, geometric thing that goes on with the picture here. So this is equal to 2 times 1 over root 2 plus I over root 2. Or, well, we already know what it is. It's root 2 plus I root 2. So here, let's say this is root 2. This is root 2 on the imaginary axis. So that's right here. Root 2 plus root 2i. Okay, but let's do some of the other roots. So how about if the k is equal to 1 root? I'll get a 2, and then pi over 4 plus pi over 2. All right, so that's 2 times cos of 3 pi over 4 plus I sine of 3 pi over 4, which, so that's 2 times, let's see, negative 1 over root 2 plus I over root 2, which is equal to negative root 2 plus I root 2. That's going to put us right here. So there's negative root 2 plus I root 2. And here, if k is equal, so I did 0, I did 1. Now let's do k equals 2. I'll go to 2 cosine of pi over 4 plus pi I sine pi over 4 plus pi. That's 2 times cos of 5 pi over 4 plus I sine of 5 pi over 4. That's 2 times, let's see, this is negative 1 over root 2, and this is also minus 1 over root 2. So again, negative root 2 minus root 2i. Which is down here. So there's negative root 2 minus root 2i. So this was the k equals 0. This was the k equals 1. This was the k equals 2. Any guess? Where should the k equals 3 one be? In the fourth quadrant, right? Yeah, okay, so I'm not even going to finish this, but maybe you can just tell. This is going to be root 2 minus root 2i, and that's going to be the k equals 3 choice. So what's the sort of beautiful geometric thing I wanted to illustrate here? These are all like exactly 90-degree rotations of each other. And that's no coincidence that in taking a fourth root, what's 360 divided by 4 is 90 degrees. So we're going to get 4 complex numbers of equal magnitude but separated by 90 degrees. And this is actually a very general pattern. If I took a fifth root, they would all be separated by 72, which is 360 divided by 5. If I took a sixth root, they would all be 60 degrees apart, which is 360 divided by 6, and so forth. So, yeah, that's kind of, that's the point that I wanted to show you with roots. Okay, so that wraps up supplement section 1 with that example. So now we need to go on to supplement section 2, which is on complex exponentials. Okay. These are pretty cool, actually. I'm a fan. I remember I was tripped out the first time I saw complex exponentials. The first time I saw like e to the ix, I was like, what the heck is that? How does that make sense, right? And, well, in pre-calculus, you guys learn what the definition of the exponential function is, right? We already know what e to the x is when x is a integer, a rational number, a negative, whatever. Any real number, we can make sense of this. And in fact, f of x equals e to the x has the nice property that its derivative is equal to itself, which ends up being super useful. So we have all these nice properties for exponentials, here's what we're going to do is, okay, I'm not going to prove to you that we're allowed to plug in imaginary numbers, because that's beyond the scope of this class. But what I will do is say, supposing that we're allowed to plug in imaginary numbers or complex numbers in general into an exponential, I want all the same rules to still be true. All the same rules for exponentials that we already learned, right? We already learned all these exponent properties back when we took algebra or pre-calculus or whatever, and all of them need to still be true. So just knowing that actually kind of tells you most of what you need to know about complex numbers. That and one other formula which I'm going to tell you, but I'm not going to prove. So you'll just kind of, for now, up until maybe you take complex analysis, which is an upper division math course, you'll just have to take it for granted. Or, you know what, maybe we'll... Here, I'll mention when we might prove it in a second, but let me tell you the formula that I'm talking about. So we will take for granted Euler's formula. Which says that if I take an exponential number to a purely imaginary number, that I can write this as cos x plus I sine x. Okay, so just believe that. You can prove this in a few different ways. One of them involves these things called Taylor series, which, has anyone already done Taylor series? Was that 20A? No, okay, we're going to do that. Okay, I should know that. Okay, we're going to do Taylor series then in this class. I got to check out my syllabus. Okay, so maybe we'll get to a point where we can prove this with Taylor series, but for now, just take it for granted. And okay, and then here's the rule. So assuming this, we can make sense of e to the z, or e to the a plus ib, for any complex number z equals a plus ib, by following all the usual rules for exponents. So, like, like what I mean, right? Z, which is, sorry, e to the z, or e to the a plus ib, well, that's e to the a, times e to the ib. That's the exponent property that e to the alpha plus beta is e to the alpha times e to the beta. So this is e to the a, which is real, and then e to the b is cos b plus I sine b. So that allows us to to take powers of imaginary numbers. And okay, I'm running out of time, so I just want to say, and I'm going to have to pick this up on Monday, that if you let x equal pi in this formula right here, you get one of my favorite formulas in math that actually I had a professor in community college who put it on his license plate because it combined all 5 of the most fundamental constants in math So if you let x equal pi in this formula, you can get e to the I pi plus 1 equals 0, right? You've got 0, the additive identity, 1, the multiplicative identity, I, the imaginary number, and then the two fundamental irrational constants of nature, e and pi, all in one equation involving addition, exponentiation, multiplication, and equality. It's a beautiful formula because it combines everything all in once. So think about that, and we'll pick it up on Monday.